Good evening. Hello.
Good evening, sir.
Yeah, good
Good
evening.
evening,
Okay.
Good
sir.
evening, sir.
Yes. So let's start the program today. If this program is about time, basically time, calendar, and things like that. Okay. So what happened is time I have done last year one program, and calendar also I had done on the New Year when on 1st January on the New Year. So this program is specifically on the textbook of ninth standard. I think yeah, ninth standard lesson number 2 most probably. So it is for the benefit of the astronomy teachers and astronomy students that basically we are doing this program. If some of you have attended this program, it's a repeat program, you can leave it. Okay. So welcome back to AFA, to the Friends of Astronomy, to the Public Astronomical Observatory. Let's have another session of learning. But before that, let me make a small announcement that on Saturday is a very interesting day, day after tomorrow. One very, very young member of AFA, young in the sense, yeah, around 25. So he is going to come and make a lovely presentation on his experiences with astronomy. He has traveled all over the world in many places, many observatories of the world, and he has done first-hand astronomy and astrophotography. So he will share his experiences and tell you about different beautiful observatories in the world and how things are going on. Okay, so if anybody is interested in becoming an astronomer, pursuing a career in astronomy, Saturday's session will be of exceptional use to all of you. Okay, so with that, let's start today's program, Movements of Earth. Okay, so we all know the basics that Earth. Just 1 second, 1 second. Videsh, recording चालू केला? Huh? Yeah. So we basically know that the Earth has basically many motions. Almost 4 to 5 motions are there, but the basic motions are two. That is rotation on its axis. In 23 hours, 56 minutes, 4.1 second, Earth goes one round from west to east. Okay, from west to east, the Earth rotates, and the Earth revolves. In the same, it revolves in a clockwise fashion around the Sun. 365.25 days it takes to make one full revolution. And this is called the year, the day and the year. Okay, and also at the same time, when the Earth is rotating, I have already pointed out to you this instrument here, the gyroscope or the gyroscope. The movement of the Earth is considered a gyroscopic movement. Okay, gyroscopic movement in the sense the Earth moves like this machine. This machine is an instrument which is used in the satellites to keep the orientation and the directions in order. So, in whichever direction you move, the axis of the gyroscope always remains fixed. So, then once you set the axis to a particular direction, whichever direction you are traveling, the axis will show you the exact direction that you want or you have marked. So the Earth is like a gyroscope. See here, as it rotates, revolves around the sun, sky, and that spot is somehow marked by the pole star. Okay. Now, as per the Kepler's laws of motion, okay, Kepler's laws of motion, Kepler planetary motion, Kepler laid down 3 laws of planetary motion, and the first law, it says that the Earth does not go around the sun, but the Earth moves around the sun in a not a round but a egg-shaped orbit. That's an elliptical orbit. Okay, ellipse is a oval shape. So you can see here the ellipse. Okay, the Earth moves around the sun in an elliptical orbit, and the sun is not at the center of the ellipse, but at the side of the ellipse. Like the circle has 2 centers, and ellipse has, like the circle has 1 center, the ellipse has 2 centers, which are called focus or foci. So the sun is at one focus of the ellipse, and the movements of Earth around the sun, okay, they decide the weather. They decide the year. The tilt of the axis decides the weather. Okay, and the rotation on the axis decides the day and night. The nearest position to the sun, when the Earth is in the nearest position to the sun, it is called the aphelion. And when the Earth is When the Earth is at the furthest position from the Sun, it's called aphelion, and when the Earth is nearest to the Sun, it is called perihelion. Okay. Similarly, there are terms for the Moon also. The Moon is also on an oval-shaped orbit, and when the Moon is nearest to the Earth, it is called in perigee, and when the Moon is furthest from the Earth, it is called as apogee. So perigee and apogee, aphelion and perihelion. Okay. So these are a few of the points which will be required for today's presentation. So remember. Okay. So we all know also. Yes.
Basically, aphelion is winter solstice and perihelion is the summer solstice.
No, aphelion and perihelion have nothing to do with seasons. Okay, nothing to do with seasons, because sometimes when the Earth is nearest to the Sun, also the winters can occur. Okay, the seasons are 100% based only on the tilt of the axis of the Earth and not with the apogee and the aphelion and perihelion of the Earth. Okay, so aphelion and perihelion have no effect on the seasons. So there is just positions which are close or far. Now see, what happens, this is a common question which many people ask. This is only asked because of this figure which I am showing you. Okay, this figure which I am showing you, see like this. I say that the Earth moves in an elliptical orbit and the Sun is at one focus, that is on one side. So you think that when the Sun is when the Earth is nearest to the Sun, the summer will happen, and when Earth is very far away, the winter will happen. But this figure, remember, is only exaggerated to show you what actually an elliptical orbit is. Okay, the Earth's orbit is not so exaggerated. This orbit, so much elliptical, is only for one planet. Can you name which planet? We already did it last session. Most elliptical orbit for which planet? Anybody? No. Last week we had done it. Last week. The most, not last week, on Tuesday, 2 days back. The most elliptical orbit is only for
Venus.
Mercury. Closest planet. Okay. The closest planet, Mercury, has the most elliptical orbit, and Venus also has. The Earth also had a very elliptical orbit, but then later on, the Moon stabilized the Earth's orbit. Okay. Anyway, what happens is, the Earth's orbit is luckily almost circular, so it is not like this. And the aphelion and the two foci of the Earth's ellipse are hardly touching each other, almost. So the Sun is, almost like this. It's slightly center or off center. So the two foci of the Earth's elliptical orbit are extremely close to each other. And if you go to space, maybe above the solar system, and if you were allowed to give a seat and sit down and observe, you would hardly see that the Earth's orbit is elliptical. Okay, it is only a slight ellipse, not a pronounced ellipse. Okay, so when the Earth is either at aphelion or perihelion in the Earth's orbit, it doesn't make much of a difference on seasons. So that is why. Okay, and as it is, the Earth is very close to the Sun also. So a little bit of a few thousand kilometers, little this side or that side wouldn't make hardly any difference to the seasons. Okay, so this is the answer. Precession also we have learnt already. Just as this top, see, this top is rotating on its needle, which is the axis of the Earth. The top is also revolving as it moves, as you know. Plus that nail here on the top, also down, is making small circles. So these circles are also caused by compounded gravitational pulls of different objects, including the Sun, the bigger planets, and so on. Okay. So what happens is, as the Earth orbits, it rotates, it revolves, it also makes a small circle at the top of its nail, the northern axis here. Okay, and this circle is called the processional circle. It takes 26,000 years to make one full circle. But the 23.5 degree tilt of the Earth is not exactly lost during this. It more or less remains the same. Only slightly it changes. Okay, slightly in and out it may change. That is another movement of the Earth which is called nutation. But that is not very important. Nutation is not considered. Okay, I have already told you about this. Fine. So there are more movements of the Earth. Okay, rotation, revolution, and precession. Rotation 24 hours, revolution approximate, and precession 26,000 years. But along with that, the Earth makes two more motions around the Sun. And what are these motions? These are called orbital, I already told you about this also, orbital eccentricity cycles and apsidal precession cycles. Okay, what is the eccentricity? Eccentricity is the shape of the ellipse, the elliptical orbit of the Earth. The more ellipse, the exaggerated or elongated the orbit of the planet is, it is called more eccentric, and the less eccentric it is called least eccentric. So the Earth is actually not very eccentric, but in a period of 1 lakh years to 41,000 years, it is a cycle. 41,000 years, then 1 lakh years. 41,000 years, it is a cycle. So in a continuation cycle, Earth's orbit also increases and decreases like a rubber band, and this is called orbital eccentricity cycle. Okay, so like rotation, revolution, precision. Now let us go bigger. These are all astronomical motions which you won't feel on Earth. Okay, so 41,000 1 lakh years are the periods of the orbital eccentricity cycle, and after this there is a even more bigger cycle that the Earth makes, the fifth motion of the Earth. Okay, that is the apsidal precession cycle. Okay, so here say this is the Earth and the Moon, which also do this movement, but the Sun and the Earth, if they were here, they would also do this motion. The entire orbit, see here, okay, the focus remains the same. The center of rotation remains the same. The Sun never changes from the focus, but the entire orbit of the Earth itself orbits the Sun. Okay, so the Earth is orbiting the Sun, and the orbit of the Earth is also orbiting the Sun. See, they are different things. Okay, and see, it is like this, like a beautiful pattern, like a flower pattern. When you complete this, it will become like a flower. So there is a huge millions of years cycles in which the Earth's orbit completes one full set of revolution around the Sun. Okay. Similarly, the Moon also has its own apsidal precession. The Moon's orbit also around the Earth is shifting continuously. This is also a reason for the eclipses. Okay. So anyway, so these are the 5 motions of Earth: rotation, revolution, precession, orbital eccentricity, and apsidal precession. Okay. So these 2 are astronomical, purely astronomical motions. You don't have to go into detail about this, but in the textbook there is a paragraph mentioning this, so you just have to know what these are. Okay, you don't have to break your head on this. 2 extreme motions of planet Earth, extreme long-term motions of the planet Earth. Okay. Now coming to more simpler and practical parts, the celestial sphere. What is the celestial sphere? Simple. The Earth is at the center here. Okay, this is a big globe. This is not the globe of Earth. This is the globe of the entire sky. Imagine you are looking at the sky now from outside. Normally what you do, you are on the Earth and you're looking up at the sky. So you are seeing a huge dome about you. Okay, a huge circular dome is there, which is called the celestial sphere. The sphere of the visible sky, visible universe. Okay, whatever you see all your life is only on the celestial sphere. You cannot pass the celestial sphere unless you have powerful telescopes like Hubble and so on. Okay, so those telescopes have powerful visions and exaggerated magnifications, which can show you further than the celestial sphere. But for us, normally, what is the celestial sphere? Whatever you see of the sky with your naked eyes, without any aids, you can say, is the celestial sphere. Okay. Now, if you would go in outside, imagine you are going outside the celestial sphere, it would appear like this. You would be inside. Okay. So, what is that? The entire celestial sphere is grouped or divided into 88 parts, and these 88 parts contain stars, and each part which contains a group of stars is called one constellation, and each of the group of stars is arranged in a particular shape, a pattern, and a geometrical figure based on ancient astronomy, mythology, folk tales, and culture. And they are given names from mostly Greek mythology, Okay, and they have on their own stories and all that things. So these are the 88 constellations which are all around you. From the northern hemisphere, you will see constellation only above the celestial equator and only very few below. From the southern hemisphere like Australia, New Zealand, you will see only the southern hemisphere constellations and only a few circum-equator, okay, circum-equatorial constellations which are near the equator, those you will see. Now, you can see this line of yellow dots here, that is the movement of the sun, the movement of the sun. You can see that the sun is not going exactly straight around the celestial equator, but cutting the celestial equator in an oblique line or a cross line. So this line on which the sun appears to move in the sky is called the ecliptic. Okay, ecliptic. This is very, very, very important for astronomy. You have to remember these two terms: celestial equator and ecliptic. Celestial equator is the equator of the earth, nothing more, projected into the sky. If you go at the equator and stand and look up in the sky, you can imagine the equator is projected like a projection, no, like a LCD projector has put a projection on the sky, and the entire sky is joined in a huge 360-degree circle, which is the celestial equator. But cutting the celestial equator, sometimes going below it, sometimes going above it, is the ecliptic, the path of the sun. And on this ecliptic, out of the 88, there are 12 constellations. Okay, out of the 88, the ecliptic passes through 12 constellations. Now, actually 13. Okay, and these 12 constellations are called zodiac constellations, Aries, Taurus, and so on. So this is the celestial equator. Okay, see, from inside, this is from outside, and now you are inside. Okay, so you are here on the earth is rotating, the entire celestial sphere is fixed, it does not move. But as you move on the planet Earth, it appears that the sky rotates. You are moving from west to east. When you are moving from west to east, the sun appears to rise in the east. Similarly, like you are sitting in a bus and the bus is going ahead. Okay, I'll give you an example. Imagine at the Kadamba bus stand, you are sitting in a bus. The bus is parked there. Okay, the bus is parked. The bus is not moving. Suddenly, the bus on the side starts moving. What do you feel? Okay, what do you feel? Or let us say it like this. So, there are 3 buses. Your bus is the central bus. And there are 2 buses on the side. Suddenly, your bus starts to move. What do you feel? You don't feel that you are moving. You suddenly move that the other buses. Yeah, it appears as if the parked buses are moving backwards. Okay, so when your Earth is moving from west to east, it is going forward. It appears that the parked universe, you can say, it is static. It is not moving. It is parked in one place. So it appears that the universe is moving backwards because the Earth is moving from west to east. Everything in the universe appears to move from east to west. That is why sun rises in the east and sets in the west. Okay. Yes. So these are the constellations and things like that. Equator, celestial sphere. Here there is the North Star or the Pole Star. Okay. One more for zodiac. Okay. Out of all the 88 constellations, we consider the 12 constellations which lie on the ecliptic only as important. It is because the sun and the solar system moves through these 12 constellations. The Earth is moving. The Earth is actually moving. The constellations are not moving. The sun is not moving. It appears that everything else is moving. Okay. So for the sun, it is an apparent motion. But for the planets and the moon, which moves through these 12 constellations, it is an actual motion. So, when you are studying time, what is time? Time is the movement of the universe. Okay, how the universe moves, how it appears to move, how you can measure it. All this is time. Time is nothing but universe, the movement of the universe. Okay, even your watch. See, what is your watch? The watch is set for 24 hours. It is set for the rotation. Your calendar on the wall is set for 12 months. That is set for the revolution. So everything that you consider whose time and the calendar is a record of the movement of the universe around you. That's all. So now, to see that, to understand the movement of the universe, we have to understand many things. One is the celestial sphere. Second is the zodiac. Third is the celestial equator and the ecliptic. One more thing we have to understand is the markings on the celestial sphere. Okay, just as the planet Earth has markings, imaginary markings, those which are parallel to the equator in circles, these are called the lines of latitudes or circles of latitudes. Okay, latitude shows you the position on the planet, the elevation on the planet, elevation, okay, or the declination. So wherever high you are, wherever low you are on the earth, high and low from what? From the equator. Okay, how high you are from the equator or how low you are from the equator is shown to you by the latitudes. You say no, at my latitude it is very hot. At your latitude it's very cold place, like that. So the higher the latitude, like Europe and all, it starts becoming colder. Okay, so see here also, the higher the latitude, South America and all, it is hotter, but at lower the latitude, it becomes cooler as you go towards the poles. Then there are the vertical lines or the vertical circles, which are called the longitudes. Okay, the longitudes. What are latitudes? Latitudes are basically your what you can say, your position on the planet, your inclination on the planet. But what are longitudes? Do you know what they are? What are longitudes? Can somebody tell me? They are lines which run. Yeah, tell me.
So longitudes are lines in north-south direction, and the Greenwich Median Time is based on the.
No. What does the longitude stand for?
Longitude.
What is the longitude?
Lines running from North Pole to South
No,
Pole.
see, listen. There is, I will fill in the blanks. Okay, longitude is equal to dash. Only one word. What you would say?
What?
Yes. No. Longitude is equal to dash. What? Sorry.
Vertical lines. Vertical lines.
No. Longitude
Imaginary line.
is equal to. Okay. Please okay.
The meridian.
Okay. No. Switch off the mics. Longitude is equal to time. Longitude is time. This is nothing but actually a clock. Okay. And I will make a statement. If you understand it. The time never moves on the earth. Okay. Remember, listen very carefully. Time never moves on the earth. The earth moves through time. Okay. Listen very carefully. The earth moves through time. For example, the sun is not moving. So wherever the sun is there in space, it is always daytime. And where the sun is not there on the other side, it is always night time. So the earth is rotating on its axis means the earth is moving through daytime and night time. Do you understand what I say? The time never moves. Okay. Daytime, nighttime, morning and evening. Okay, dawn, dusk, noon and midnight. These four coordinates of time never move. Okay, in space around the earth, it is always afternoon, night, evening and morning at the same places. It is earth that moves through these four divisions of time. Okay, and the same divisions of the earth, the latitudes and the longitudes, if you project them in space on the celestial sphere, they become right ascensions and declinations. Okay, so declinations are the latitudes of the celestial sphere and right ascensions are the longitudes of the celestial sphere. Just as latitudes and longitudes are used for telling us time and movement of any object on the earth, similarly the right ascension and declination are used to show the position of any object in the universe. So if I give you a particular right ascension and declination, immediately you are able to tell me which object of the universe I am talking about. So that is what astronomers learn. Okay, right ascension and declinations of all the objects in the universe. And you don't have to by heart them. There are tables for that. There are tables. Okay. So see here. Okay. So let us put now into whatever we have learned in theory. We'll put in practice. This is the celestial sphere. Okay. At the center is the Earth rotating. The north pole of the Earth projected on the celestial sphere is the north celestial pole, and the south pole of the Earth projected on the celestial sphere is the south celestial pole. Fine. The equator of the Earth projected on the celestial sphere becomes the celestial equator, and the north hemisphere, whatever you see in the sky, is the northern celestial hemisphere, and the southern hemisphere, whatever you see of the sky, is the southern celestial hemisphere. This is the celestial sphere. Now we have completely finished this part, celestial sphere. But now what happens? The Earth is actually not standing 90 degrees. The Earth is not standing 90 degrees. This plane of rotation of the Earth, see the celestial equator, the plane of the celestial equator is not actually round and flat as it looks. It is tilted. I think I have a picture for you here. Yeah, here, see. Okay, you think the Earth is like this, but actually the Earth is like this. It is tilted. Okay? It is tilted. So what happens? The sun, actually the sun is what, for us the sun is actually moving like this in a straight line. The sun is moving on the solar system, the plane of the solar system, which is actually flat, which is parallel. But because the Earth is tilted, it appears to us like this. It appears that we are standing straight and the sun is going up and down. But actually the sun is not going up and down, we are tilted, and this is how it is. Okay. So the celestial equator and the path of the sun, the ecliptic, is dissected at 2 points here. Okay? In the sky, they meet at each point here. Here the celestial sphere and the ecliptic meet here and here at 2 points. And at 2 points, they are the furthest from each other. See, there is the huge distance, the maximum distance and the minimum distance. And all these 4 points are very important. These points are called the points of the equinox and the points of the solstice. Earth is moving in the center, and the place where the equator of the Earth and the ecliptic, the path of the sun, meet, there are 2 points. This is called vernal equinox. So this is 21st March. The sun comes exactly at this point. Now it doesn't come, but previously it used to come. On 21st March, the sun comes at this point, and when the sun touches this point, okay, the sun is now on the ecliptic, and the sun has risen like this, and sun has touched here on the ecliptic. Today, the sun is shining on the point of vernal equinox. Now tell me, if you are standing on the Earth, on the celestial equator, okay, on the poles and on the poles and on the tropics, equator, you are one of you standing at the equator, one of you is standing on the Tropic of Cancer, and one of you is standing on the North Pole. On the vernal equinox, who will see the sun exactly on his head? The person at the equator, a Tropic of Cancer, or North Pole, will see the sun exactly at the top of his head. Equator. Okay. So the person standing on the equator will see the sun exactly on his head. Why? Why?
Wait.
Why? What is the
Because the sun is shining exactly on the equator.
Yes, correct. Exactly. Very good. Excellent. Okay. Because the day the sun comes on the vernal equinox, it also shines exactly on the equator. So the sun shines on the equator, celestial equator, only on 2 days of the year, 21st June, 21st March, and 21st or 22nd September. They are called the vernal or the summer or the spring equinox and the autumnal equinox. On those days, they have equal days and nights. We all know that. Okay. And on the days when the sun is highest in the sky, it is the summer solstice that happens in June. Okay, and when the sun is lowest in the sky, it is winter solstice. It happens in 22nd December. So these are the 4 cardinal points of the celestial equator, and this is the foundation of seasons. Okay, so we already did this. Now we will see about rotation. The concept of time was discovered by our ancestors. When they looked at the sky, when they saw the shadows of the sun, they started understanding that the sun is moving in the sky, and as the sun moves and sets, it is not the new sun which rises tomorrow, it is the same star sun which is rising the next day. It is a cycle. When they understood the meaning of this cycle, understood the meaning of the day, 24 hours, daytime, day and night. Okay, our ancestors were the first to comprehend this part of the movement of time. Now, what are time zones? Okay, we know now what is time. Time is the movement of the universe. What are time zones? Time zones are nothing but markings of the celestial pole, celestial sphere, or markings also you can say on the Earth's globe. Okay, so the longitudes of the Earth. Okay, the longitudes. What are the longitudes? I told you they are time. They are time itself, and they are also called the time zones. Okay, how does the Earth move in 360 degrees can be understood very clearly by understanding the longitudes. Okay, the Earth is circular, it moves by itself, so in one rotation it will cover 360 degrees. At every degree that the
Excuse
Earth
me,
moves
sir.
yeah, tell me. Yes, hello. Any question? Okay, so at every degree that the Earth is moving through is one particular time. Okay, how shall we understand this? Very simple. See, the movement of the Earth is 360 degrees. Can you put off your mics, please? It is causing a disturbance here. Yeah. So the Earth, now look carefully. Okay, this is a very fundamental thing of time. The Earth is moving to 360 degrees. The Earth takes 24 hours to move through 360 degrees. So 360 degrees divided by 24. Okay, so those are the time zones. So it is 15. The answer is 15. So there are 24 time zones of 15 degrees each. So every 15 degrees there is one time zone. Okay, and each zone is called a longitude. It is a time zone. Also, between two lines of longitudes, there are smaller 14 longitudes. Every 2 longitudes between them contains 14 smaller longitudes, which are called meridians. Okay, which are called meridians. So 14 meridians. How many are there? 24. How many longitudes are there? There are 24 longitudes. So yeah, 24 longitudes. So between these 24 longitudes, there are 14 meridians each. So 14 multiplied by 20. So plus 24. Okay, so 336 degrees plus 24. What is the answer? 360. And what is 360? The circle, the complete circle. This is how, see, exactly, it is the geometry of time. Okay, geometry of time. Let's go over again. The Earth moves 360 degrees in 24 hours. So per hour, the Earth moves 15 degrees forwards. 15 degrees forward. Every 15th degree, there is one line which is called the longitude. Between these 24 longitudes, there are sub-longitudes which are called meridians. Okay. So how many meridians are there? 14 into 24 groups, 336. How many longitudes are there? 24 longitudes. 24 into 1 is 24. 336 plus 24 is 360. This is the exact circle, 360 degrees. This shows you that the earth is moving around itself in 360 degrees in 24 time zones. And what are these 24 time zones? They are the 24 hours of the clock. Okay, so the earth is like a clock. Other clock is like earth. If you have a 24-hour clock on your hand, our clocks are only of 12 hours, but if you have a 24-hour clock on your hand, you will exactly understand how the earth is moving between the 24 time zones. Okay, meridian. Okay, so when the sun is on top of your meridian, you might be at any point on the planet Earth, okay, but there will be a, because see, every 1 degree there is a line on top of you. At every 1 distance, 1 degree, one line, another degree, the second line, third degree, another line. So every degree distance of the earth, from every degree onwards, there is one line on top of your head, which is your meridian. Everybody is standing below one meridian. Okay, so what happens is, whenever the sun shines exactly on top of your meridian, for you it is afternoon or midday, not exactly at 12 o'clock. The sun doesn't shine at midday everywhere at 12 o'clock. Okay. But wherever you are on the planet Earth, when the sun shines on top of your head, that is your midday. And before the midday it is called AM, and after the midday it is called PM. Simple meaning is, what is AM? Anti-meridian, because before the meridian. And what is PM? Post-meridian, after the meridian. Okay, so when somebody asks you the time, what is the time? And you say it is 3 p.m. What does it mean? The sun has moved 3 meridians after my meridian. Okay, when you say the time is 10 a.m. 10 a.m. means in 2 more meridians, the sun will come on my meridian and it will be noon for me. Something like that. Okay. So anti-meridian, post-meridian. When somebody is asking you the time, and when you are telling them that the time is AM and PM, what you are actually talking is astronomy. AM and PM. You are actually telling him in secret code how many meridians away the sun is from you, or how many meridians the sun has already crossed and passed away from you. This is what is the astronomical meaning of AM and PM. Okay. Now Greenwich. Now the Earth, so many meridians. So from where shall we start counting time? We need a specific place to count time. Okay, we can't start counting time from anywhere. Long ago, every country had, most of the countries had their own time zones. They said 12 o'clock is starting in my country. Some countries said 1 o'clock is starting in my country. Okay, so every country had some egoistic attraction to having the time starting from their country. So what happened is, in the year 1884, there was a conference of geographers. Okay, it is still held in intervals. It is called the Meridian Conference. So they had a Meridian Conference in 1884 in Washington, and there they decided that we cannot have different time zones for different countries. Let's do something where the Earth, let's have a constant time for the entire Earth. Okay. So what they did, they decided to put the boundaries of time at the Greenwich meridian. Okay, the meridian which was passing above the Royal Observatory of Greenwich. The Royal Observatory of Greenwich is outside London. It is very famous, and even King Charles II had done a lot of observation from that observatory. It is a very famous observatory. A lot of astronomical discoveries in ancient times, in medieval times, were done from the Greenwich Observatory. When you go to UK, you can visit this observatory and see for yourself. It's a very beautiful place, and this is the place which marks the center of time, the starting of time. See here in the Greenwich, when you go there, there is a nice, there is a practice, there is a custom of taking this photo. So when you place one hand, one leg here and one leg there, here you are at 1 o'clock and here you are at 12 o'clock. You are here into today and here you are into tomorrow, yesterday. Okay, so you are at two different time zones because the Greenwich meridian starts here in the middle of Greenwich Observatory. Okay, so from here, this is Greenwich here at the center here. See, this is 0 degrees and going ahead 1, 2, 3, 4, passing, going towards the east and coming from the west. So from here 0. So here 1, 2, 3, 4 will start, pass around the earth and it will come here 22, 23, 24 will end here. So this is time zone, central time zone of planet Earth, which is maintained at the Greenwich Observatory. Okay. In India, we have the Indian Standard Time. What is Indian Standard Time? In the British times, okay, India, they were having time centrally marked at Calcutta. But Calcutta falls on the eastern side of the country. And when the time at Calcutta is something, the time in Gujarat is something else. Okay, because I have observed, I am staying on the western coast in Goa. For the first time in my life, I went furthest north, okay, furthest northeast, and I went to Patna. And we went to Patna in the morning, we reached there and all that, and we went to sleep in the afternoon, we were taking a siesta. We thought like Goa, we will get up at 5 o'clock and go out for sightseeing and all that. But when we got up at 5 o'clock in the evening, we were shocked. It was dark at 5 o'clock. In Goa, it never becomes dark at 5 o'clock, but in Patna, it became almost dark, and within 15 minutes, the night started. Okay, it was winter. We did not realize the time zone. Okay, because Goa to Calcutta, Tripura is different. The time zones are different. So to have a constant time zone, constant all over India, because India is a big country from Gujarat to Calcutta. So you cannot have different time zones for the same country. Okay, Russia has, I think. Russia used to have once upon a time, but now they don't have. Okay. So see, Russia is here. It was such a big country, USSR. The countries at this side and the countries at that side were in different time zones. So you could not have the same time zone for the entire country. They had different time zones. It makes administration very difficult. So the Indian government decided that 82.5 degree latitude, okay, and 5.5 degrees of longitude, there we will mark the time zone for India. So the location was marked at a clock tower which exists at Mirzapur in Uttar Pradesh. Okay, it is at 82.5 degree latitude and 5.5 degrees of longitude. Okay, this exact spot of the clock tower of Mirzapur marks the latitude for Indian Standard Time. Indian Standard Time is 5.5 hours ahead of Greenwich Meridian Time. Okay, when I say that IST is 5.5 hours ahead of GMT, what exactly do I mean in astronomy? Can somebody tell me? Let us see how much you know. This is a very technical topic. Huh? It is called horology, the astronomy of time. So anybody can tell me when I say that India is 5.5 hours ahead of time. Indian Standard Time is 5.5 hours ahead. Ahead of what? Greenwich. But what exactly do I mean by 5.5? Can you tell me?
Greenwich Meridian Time.
5.5 meridians.
Longitude, exactly, correct. 100%. Okay, excellent answer. Excellent. Okay, so India is 5.5 hours ahead of the longitude of GMT. That is what it means. See here at the center. Okay, here is 0. Okay, so 1, 2, 3. No, here it is. 1. This is 1, 2, 3, 4, and 5 here. 5.5. Calcutta is almost at 5.5 here. Okay, so India is almost 5.5 longitudes ahead of the Greenwich meridian. Greenwich is here. Okay, so this is what it means. Also, another small data for you. Always you see that the map of the earth is marked like this. The earth is a circle. The earth is a circle. Earth is round. You no need to mark it like this. Okay, you can even put India in the center. You can put America in the center. But 99% of all cartographers, map makers, make the Earth's map look like this. Do you know why it is? It is simply because of the reason that this line is the Greenwich meridian, 0 degrees, and it is compulsory as per the meridian conference that it has to come at the center of every map. Okay, it's a rule laid down for it. That is why it is like that. It is not like this just by chance. Okay, and this also line at the end of this map also represents something extremely important. Do you know what? This line at the end of the map, this entire edge of the map also represents something very, very important and crucial in timekeeping. Do you know what this outline, the entire outline of this globe, do you know what is the name for this outline? Let us see how much geography you know today. The central line is the Greenwich meridian. Can you tell me what this line is? The entire line, which is the border of this map. Do you know what it means? What is the name for it? Nobody? Okay. So this is GMT. The center is GMT. Okay. And the edge is called IDL. It is called the IDL. Let us see what is the IDL. Okay. See, it is the international date line. Exactly opposite the Greenwich meridian line here. The other line 180 degrees behind it is the second part of the circle of the 0 degrees longitude. Okay, the front half of the 0 degree longitude passing through Europe and Africa is considered the GMT, and the other next part of this circle, which is on the other side going through the Atlantic Ocean here, sorry, Pacific Ocean here, is considered the IDL, International Date Line. Okay, here. If you go west of this line, you lose a day. But if you come east of this line, you get an extra day. Okay, it is like that. Somewhere in this, I think, Hawaii, no, not Hawaii, somewhere in the Polynesian Islands, some of these islands, just like the Greenwich Meridian is shown at the Greenwich Meridian Observatory in Greenwich, they try to show the line on like this, and they say that when you take a photo here, there are tourists. Okay, you are standing on the night yesterday, and you are standing on today. But actually, it is not so, for the simple reason that this line, the IDL, never passes through any land. Okay, the IDL compulsorily passes through only water. And here you can see that if the IDL is passing like this, it has to pass through some land masses. And this is avoided by only one line of the meridian is given an exception. And this IDL is given the exception. It is given the permission to become zigzag. Okay, so this is the zigzag line. It is not a straight line. Can you tell me why it is zigzag?
So it does not
So it
touch
is
any.
only closest to
Yeah,
water.
the person who said first, the person who first, tell me first. Okay, others put off your mic. The first one, yeah, go on. I didn't say the name, but the person who spoke first can tell me.
So because it should not touch any land.
Excellent, excellent. Yes. Okay. Very true. Very true. Imagine the ideal is through Santenis. Okay. Or maybe I will say the river is a passing through Fire River. So Madgaon is yesterday and Panji is in today. If I'm working in an office in Madgaon, every day I will be going from today to tomorrow, and every evening I will coming from tomorrow to today. Okay, so it will be crazy. My watch will go crazy. I will also go crazy, keeping the calendar. So you cannot continuously move from today to tomorrow. One landmass, one country cannot be in two different calendar zones. Not just time. Now they are date zones. It's a date changes here. So it becomes crazy for people to remember this. That is why that is a special exception is given by the Meridian Conference to the IDL so that it might be zigzag and it's flexible. It can be changed anytime you want. So if this country wants to come on this side or this island wants to go on that side, they can request the Meridian Conference to do that, and the Meridian Conference will again change the zigzag and put them on either this side or that side. Okay. So people who are on one side of the ideal always follow the American economy, and people are on the other side follow the Japanese economy. That is how it happens. Okay. Now, type of days. There are different type of days. Now it's a little technical. Okay. So simply listen to what I'm saying. The sun rises in the morning, the day starts. The sun sets in the evening, the day ends. Actually, the day ends. Next day, when the sun again rises, one actual day is over, which we divide as day and night. So actually, the day is 24 hours. Okay, even the night is a part of the day. Actually, a day doesn't mean sunlight. The day is a 24-hour cycle of the Earth around its axis. Okay, so there are different type of days followed in astronomy. First one is a civil day, or simply a calendar day. Okay, the calendar day of the Earth is the period of time during which the Earth completes one rotation, 360 degrees on its axis. Okay, it is broadly divided into 12 hours of day and 12 hours of night. Approximately, people believe that 12 o'clock afternoon is the afternoon and 12 o'clock night is the midnight. Approximately. Okay, so it is more or less a thing of convenience. It is more or less a thing of convenience. That is why it is called a civil day. Civil day, to make life easier for us. Then there is the solar day. Okay, solar day is exactly the period that the Earth takes to make one exact rotation relative to the sun. Okay, because what happens? Say, for example, today at 5:30, 6:30, the sun has risen. But tomorrow, exactly at 6:30, again the sun will not rise at the same spot because of a simple reason: the Earth is also revolving. The Earth is also moving ahead in its orbit. That is why this point where the sun was seen exactly yesterday will not be the same today. There will be a slight difference. It will take little more time, 1 degree more. Okay, so that is why a solar day is slightly more than a civil day. It is the astronomical time from which you can see the sunset at the same point on Earth. Again, the sun is rising here in front of Kolwa Beach. Tomorrow, if the sun has to rise at the same point at the same time at Kolwa Beach, it will not rise at the same time. It will rise at the same point, but it will never rise at the same time. It will take hardly 1 second more, a little time more. Okay, so that is because the Earth has revolved ahead in its orbit. So, as the sun moves across the sky, that is the actual practical practical proof of rotation. But how will you get a proof of revolution? The solar day will give you the proof of revolution, because the sun will never at the same time at the same spot every day, because it has to go on, it has to move on in the orbit. So this is a solar day. Then we also have a sidereal day. Sidereal means star. So now this is more complicated. Okay, this sidereal day is the day taken to make the sidereal calendar. Sidereal calendar is a seasonal calendar. We make seasons. So when we make seasons, we have to have everything ultra accurate. We cannot make mistakes when calculating season. Ultra accurate. So that is why not just the sun is taken to mark a sidereal day. How they mark it? They take the position of the sun along with the distant star. Okay, so today you are standing here. So the sun is there, and behind the sun, a star is there. So the exact line is marked. In 24 hours of rotation, will the sun again be at the same position and at the star will be at the same position? Will both match each other? No, they will differ. Okay, because the Earth has moved ahead, the sun has also shifted in the sky, but the star is remained fixed. Okay, so on the second day, the sun has moved a little backwards. Okay, and the sun has adjusted itself for the solar day, but the solar day is not fully accurate. For the astronomical calculation, we require a sidereal day. Okay, so the point where the Earth exactly comes again in front of the same star at the same time is called the sidereal day. So Simply on convenience, we have the civil day. Based on the sun's position at rising, we have the solar day. And based on the position of the stars in the sky, we have a sidereal day. But we don't follow this so detailed. These are only astronomical calculation, time zones. These are not followed by us in day-to-day life. Okay. Now we finish the rotation and the effects of rotation, the days. Now let us see the revolution. Okay, so we already said this is fast. It will finish fast because we already saw this. For most important thing for the seasons to happen is the tilt of the earth. Because the earth is tilted, the sun appears to be tilted. We feel that we are standing straight. Okay, the sun seems to set and the sun seems to rise just because the earth is tilted. And because the equator of the earth, celestial equator, and the sun's path, the ecliptic, is tilted to each other at 23.5 degrees. Why is the difference here 23.5 degrees? Simply because the earth is tilted at 23.5 degrees away from the sun's plane. Okay, it is geometry. Because the earth is tilted 23.5 degrees away from the sun's of solar system, that is why the sun also appears to rise and set maximum 23.5 degrees. So only at 23.5 degrees above the equator and 23.5 degrees below the equator, you will see the sun on top of your head. So this is the place, equator and the Tropic of Cancer and Tropic of Capricorn. These 3 points, the place, the countries, the area between these 3 lines is the best for living. This is the most comfortable life people have is between the Tropic of Cancer to the Tropic of Capricorn. This is the most comfortable zone of the earth. It is called the tropical zone. Okay. Above this and below this, the sun never rises up or straight. You always see the sun tilted, slanting. So that is why these areas above the Tropic of Cancer, below the Tropic of Capricorn are cold areas and not 100% comfortable areas. Everything doesn't grow there, okay? But everything grows here at the tropics. Everything grows at the tropics, but everything doesn't grow at those places. And the seasons also are prolonged and painful. The cold is too much at these points, okay? Beyond the tropics of the earth. That is why we here, India, staying at the tropics are the most comfortable. See, by the time you reach Kashmir, it becomes miserable. Okay. Yes. So, let us see the seasons. When the sun is directly touching the equator, it is the vernal equinox, 21st March. Okay. On that day, what will happen? The sun's rays will directly shine parallel to the Earth's equator. Okay. The entire planet Earth will receive equal amount of sunlight for the entire duration of 12 hours. Okay, equal amount of sun rays. So there is equal day and equal night only on these days on 21st March and 22nd September. Also, on these days only, 21st March and 22nd September, the sun will rise on the east and the sun will set in the west. Only on 2 days of the year, the sun rises in the east and the sun sets in the west. For all other days of the year, the sun either rises in the northeast or the southeast. It never rises in the east, actually. We say, no, sun rises in the east, sun sets in the west. Actually, it is wrong. The complete statement should be, the sun rises in the east and the sun sets in the west only on 21st March and 22nd September. Okay? Yes. Now, the sun has moved. From the equator, the sun has risen up to the maximum point on its orbit. It cannot go ahead. It cannot go more up. It is now at 23.5 degrees above the celestial equator. So also it will be appearing 23.5 degrees above the Earth's equator on the Tropic of Cancer. People living in Madhya Pradesh, in India, will experience the no shadow day when the sun is on their latitude on 21st June. What happens on 21st March at the equator happens on 21st June at the Tropic of Cancer. Okay, this is called the day of the summer solstice.
So,
Yes.
so Jantar Mantar and Abus clocks will not work if they are situated in Madhya Pradesh, right? On
No.
21st March.
Listen. The Jantar Mantars are observatories for which there are instruments are common, but in every Jantar Mantar, the instruments are calibrated for the latitudes and longitudes. Okay, so wherever they are situated, Jantar Mantar in Madhya Pradesh, Varanasi, even one is there in Haridwar, all of them are calibrated for that latitude and longitude. So that correction is done in the instruments while constructing them. So you need not worry. Wherever you go and whichever Jantar Mantar you visit, it will always be accurate, because all the instruments are not like made in a factory and put there. Each instrument is manufactured for that observatory only. It is one of its kind, unique instrument. Okay. Yes. So summer solstice 21st June. Sun is exactly at its maximum distance above the equator, 23.5 degrees. What happens here? Today the sun will shine exactly on the Tropic of Cancer, and because of that, unequal areas on the earth will receive sunlight. That means that the southern hemisphere will receive less sunlight, the northern hemisphere will receive more sunlight, unequal amounts on the solstice day. Okay, and what happens is the North Pole comes in complete daytime and the South Pole goes in complete nighttime from this day. From this day, there will be 6 months of darkness here and there will be 6 months of daytime here. Okay, see here, beyond this line, the Tropic of Cancer up till the North Pole, life is not very easy. Okay, check out the life in extreme Canada, Siberia, then here down also. Okay, down extreme New Zealand, life is different. Life is very different. Okay, it's not as comfortable as you think it is in this zone, the tropical zone. Okay, so now the sun has moved from here and it has in 3 months come to 22nd September. It is the autumnal equinox. Equinox means equal night. Now again the same thing that happened 6 months back happens again. No difference at all. Only that the date has changed from 21st March to 22nd September. Remaining everything else is the same. The sun again shines sharp on the equator because now the sun has moved from its journey. It has touched the equator again, and after this day, the sun will start shifting downwards. See, in 3 months of the autumnal equinox, we come to 22nd December, the winter solstice, the coldest day in the southern hemisphere, northern hemisphere, hottest day in the northern hemisphere, when the sun shines directly now on the Tropic of Capricorn. So for the southern hemisphere there is summer and for the northern hemisphere there is winter. The Arctic night starts now and for 6 months it will be night here, and the Antarctic day starts now and for 6 months there will be daytime in Antarctic. But the sun will never be on top here. It's not our daytime and nighttime. The sun will always be a little above the horizon and moving round and round near the horizon. If you go to Arctic or Antarctic, it is a very, very funny sort of feeling that you get when you look at the sun, because the sun can never rise above. Okay, it hardly is. And it is still because the sun is up, the sun is very slanting, so still it is quite cold. Okay, when I say that the sun is moving from here to here to here, what do I mean? I do not mean that the sun is actually moving. What is actually happening is this picture. Look carefully. When the sun is, say, November, when the earth is in November, okay, from the we can see the sun here and the background we can see Libra. So that is why the sun, we say, is in Libra in November. But in 2 months, when the sun has moved, earth has moved ahead in its orbit and gone to this position in January, the sun is here fixed, the constellations are fixed, but now suddenly the point of view changes. So it appears The sun now doesn't shine in Libra, now the sun shines in Sagittarius. So it appears that the sun has moved. So this is what we are saying when we say that the sun is moved. The sun never moves. Okay. We in astronomy call the movement of the sun apparent movement. It is not an actual movement. Only the earth has an actual movement from here to here. What everything else remains stationary. Only actual movement is of the earth, everything else is apparent. Okay. One more point of importance in geography. When we are talking of Tropic of Cancer and Tropic of Capricorn, what are the meaning of these words Tropic of Cancer and Tropic of Capricorn? These lines are named as per astronomy. So when you understand astronomy, geography becomes very easy. Okay. So I already told you, on 22nd June, the sun rises at the highest point in the sky, and that time the sun appears in the constellation Cancer. So when you stand at the equator on 21st March, the sun will appear in Aries, the vernal equinox. Okay. But when you stand here on the Tropic of Cancer, on 21st June, the sun will appear in the constellation Cancer. That is why it is named the Tropic of Cancer. The Tropic of Cancer is the point beyond which the sun cannot move. Okay, so the sun can only move between the constellations of Cancer to Capricorn. Down, it is Capricorn. Okay, so maximum the sun can move is the Tropic of Capricorn. Below. So on this day, 22nd September, when the sun can be seen overhead, exactly on top of your head, on the Tropic of Capricorn, in the background, you will see the constellation Capricorn. So that is why these constellations are named Tropic of Cancer, Tropic of Capricorn. Now actually this thing has changed. The sun does not actually appear on the Tropic of Capricorn on 22nd September. On 22nd September, the sun appears not in Capricorn, but it appears in Sagittarius. Can you tell me why? Nobody? Okay. Because precision, yeah. Because 2000 years ago, when the calendar was made, they observed that on 22nd September, December, on the highest point of the sun was in the constellation Capricorn. So they named the line Tropic of Capricorn. But now we have observed that the axis of Earth itself has shifted. So a slight shift of 2 degrees has already happened, and the sun has slided down into the constellation Sagittarius on the day of the winter solstice. Okay, so all these things are part of the revolution of the Earth. Now, finally, the last point: types of years.
So
we saw the types of days. Okay, any question?
yes, sir. So precession also has a part in playing in a change of times of seasons, right? Like the delay in seasons, etc. And because precession.
Yeah, I didn't get your question. I didn't get you.
The precession, it also has a part in the delay or arrival of time of seasons, right?
Exactly. Precision directly has an effect on the rotation causes a day, revolution causes some year. What does precision cause? Precision causes the shifting of stars in the sky, appearance shifting. It appears to shift because the Earth itself is shifting. Okay, and secondly, it causes the shifting of seasons because you are accustomed that when the sun shines in the Aries, the summer will start. But now the summer will start when the sun shines not in Aries, but the sun shines in Pisces. So the entire orientation of the season changes. Also, many scientists are now considering, although it might also be because of El Nino or La Nina effect, they also consider that the winter has shifted 1 month and the summer has shifted 1 month. Okay, so actually the height of summer is not in May, but it is in June. It is hotter in June than in May. You experience this. Okay, and it is colder in January than in December. Previously, December was winter, but now January is winter. January is colder. Even the monsoon has slightly shifted. So all the shifting of seasons is caused by precession. It's very true. Okay. So calendar. Calendars are purely based on two things. One is culture and religion, and second is astronomy. Okay. So this is the lunar calendar. Lunar calendar is based on the cycles of the moon. The moon takes about 27 to 30 days to come around, make one full cycle of the earth. Okay. So by the time the moon makes 12 circles around the earth, it is called a lunar year. This lunar calendar has only 30 into 12 days. So 330. It doesn't have 360 days. It has only 330 days. And only one type of people follow this lunar calendar today on earth. Who are those?
So
Can you
Aztecs,
tell me? Sorry?
Aztecs,
No. Who follow the lunar calendar?
The lunar tribes.
No.
Chinese.
You will be very intelligent. I think some of the people who follow lunar calendar will be sitting for this program.
The astrologers.
also the
No.
Jews. So the
Astronomers.
Jews.
Muslims. It is called the Hijri calendar. Yeah, the Muslims follow the lunar calendar. Okay, that is why. The Jews also follow the lunar calendar. Okay, but see, the Jews have a correction. I think the lunisolar correction. I don't think the Muslim calendar has the correction. Okay, what happens is, because the moon has only 30 days for 1 month, and in 12 months it doesn't complete 365-degree circle of the sky. What will happen? The sun will not complete the full rotation of the earth. The earth will not complete one full revolution around the earth, which takes 365 degrees. Okay, so that is why the lunar calendar will remain backwards and the seasons will start shifting. So every 3-4 years there is a correction to be done. Okay, in India, Hindus follow lunisolar calendar, another type of year. What happens in the lunisolar calendar is the Hindus still follow the 30-day months like the Muslims, but every 3 years, because the months are shifting backwards, they add an entire 30-day month to balance the 365 days of the sun and make it a leap month. Like the English have the leap year, leap day. We have the leap month in India. The calendar balances itself, and again the seasons fall at the same time. Okay, that is why Ganesh Chaturthi always falls in monsoon and so on. Diwali always falls in winter, but Eid does not always fall in the same season. Okay, so the Jews, I think, have this correction like the Hindus. When they put it back and the calendar is connected and synchronized to the seasons, but the Hijri calendar, the Muslim calendar, does not have the correction. It goes ahead and every 330 days it follows, it completes 1 year. Okay, that is why there is a slight shifting of Eid from here to there. But I think the Hijri calendar also has a minute correction. I am not very much expert in that. I think they also make a slight correction. Otherwise, it would go on shifting backwards. Okay. Yes. Then we have the tropical year and the common year. Okay. What is a common year? A common year is a civil year, like we have the civil day. It takes 365 days. That is all. 365 days. Around 365 days. But 1/4 day is short. Because you cannot have your new year. Okay. See, if you did not follow the common calendar, we all follow the common calendar, the common year. If you were not following the common calendar, you would be in trouble. For the simple reason that on 31st December, the new year would not come at 12 o'clock. It would always come 3 hours ahead. So at one point of time, you would end up celebrating New Year at 5:30 in the morning also. Okay. So to avoid that, they have the common year. And every 3 years, they correct the year by putting 1 day. 1/4 is 1 full day. Okay. Now we have the tropical year. The tropical year is 365.24. It is one complete orbit of the Earth by the Earth of the Sun. So this is exact. It has to come here. So see here, it is shown here. Here, the Earth has not yet come to the exact position. It is short by 1/4 day. But the tropical year does not consider that. So the tropical New Year will always be different. Okay. So the year that is more astronomically correct is the tropical year. So This is the two main calendars. Then, like the sidereal day, we also have a sidereal year. Okay, so we take a star in the sky, say 1, star position 1, and to start the tropical year, sidereal year, what we do, we see that they are in a straight line. We complete 365 days, but even after completing of 365 days, we find that after 365 days exactly, the sun has, the star, the sun and the earth have not yet aligned in the same direction. To make this alignment, the sun has to travel a little more of 20 minutes. So after 365 days, 365.14th day, year, it still has to travel 20 minutes more to again match the star in the sky. So this 365.242 days and 22 minutes exact is the sidereal year or the astronomical year. Only astronomers follow this. Okay. Yes. So this is the common year and the leap year. The common year is the year of 365 days. But in the leap year, what happens? The day exceeds by 1 day. So 3/4 day is over. The year is 366 days, which is a little more than what 3/4 more than what it actually takes for the sun to come back to the same position. Okay. So if we go on taking the leap years like this, in millions of years, what will happen? Again, the position of the earth will be lost. This correction of leap year is not actually accurately correct. So you know that in some years, a big year, like big gaps of 1,000 years, like 1,000 years, million years, we have to drop 1 day from the calendar. Just as you add a leap day, we have to drop 1 day and the calendar has to become of 364 days. But it is an extremely rare phenomena. It will not happen in our lifetimes. Okay, where 1 year will be short of 1 day to adjust this mistake. We have the civil year, the story of the civil year. I'll go through this fast only because it is there in a small note is there in your textbook. So I'll just cover it very fast. The calendar that we follow today is the Roman calendar. Okay, and before that, the Romans borrowed it from the Egyptian. It was a solar calendar. The Egyptians had a solar calendar of 365 days. But the Romans had a lunar calendar. They did not match each other. So it was Julius Caesar, okay, who brought the calendar of Egypt into Rome and made the Julian calendar. The Roman calendar, before the calendar was modified by Julius Caesar, the month of the Romans started from March, not from January. It started from March, and all they had 12 months which were named after their gods. Okay, March, the new year started with March, named after Mars, the god of war. Okay, then it started, the next was April, from goddess of spring. May, the goddess of summer. Okay, then was June, the goddess of rain, monsoon. Then we had, after these 4 gods, the other 5 months were only numbers. They were only numbers. Okay, they were called quintilius, sextilius, September, October, November, December. Okay, so quint means 5 in Latin, sext means 6 in Latin, sept means 7 in Latin, and so on. So quinta, sexta, septa, octa, nov, and des were 5, 6, 7, 8, 9, 10. Okay, so these were the 5th, 6th, 7th, 8th, and 9th month. So December was des.
10.
Not 10. Okay, why it is so? Later. Okay, what happened is the 11th month of the Romans was called Januarius, after the god Janus, who is the god of good luck. And the Februarius, the last month, the 12th month, was named after the god Februus, who was the god of hell. So Janus was the god of heaven and Februus was the god of hell. So these were the 12 months of the months. They also found that the match seasons were not matching. So every 3 years after February, they added one entire month to the calendar. And for only 1 year, after 3 or 4 years, they made it a lunisolar calendar and they called that month Macedonius. Okay, Macedonius, it was added after February. still that practice has been continued. Even though the new year is now celebrated in January, the leap day is never added in December. The leap day is added in February. This is the Roman custom because the leap month was added after February. Okay, that is why 29th March, February is always added here, but it is never 32nd December. Okay? So this is it's a culture, it is a heritage which we have borrowed from the Egyptians to the Greeks to the Romans. Okay, so Julius Caesar in the 1st January 45 BC, he reset the calendar and followed the Egyptian calendar. From the lunar calendar of the Romans, he made the 365-day solar calendar, which is now somewhat borrowed and we are using it today. Okay, in the year 44 BC, the 5th month of the year, Quintilius, was, they decided that let us remove the name 5 and let us make the month more romantic and let us name it after our king. So in the year 44 BC, the name Quintilius was removed and the month was named Julius. Okay, why? Because it was the month which had the birthday of Julius Caesar. So the month was named in his honor. Okay, after Julius Caesar died, his nephew, who was an equally great person, Augustus. Okay, Augustus Caesar became the emperor of Rome. Okay, so the followers of Augustus Caesar named the 6th month Sextilius. They renamed the month into Augustus. Why? Because his birthday, not birthday, his death anniversary fell in the month of August. Okay, this month was the death anniversary of Augustus Caesar, the emperor of Rome. So that is why they named the month Augustus. This was fine. Naming Quintilius and Sextilius as Julius and Augustus was no problem. But then something strange happened. Okay, in Rome was a democracy. There was a ruling party and an opposition party. So the ruling party was the followers of Augustus. So what they did one strange thing. They said that Augustus cannot come after Julius because it will be an insult to the emperor. So you can't come after Julius Caesar. We will put his month before Julius Caesar. And strangely, in 1 year, August came first and July came next. Then what happened? Do you know what happened afterwards?
No, sir.
Then there was a war. Okay, the opposition and the ruling went for war, and people died on the battlefield. They killed each other for the calendar. Okay, there was a fight, there was a bloodbath, and finally there was a treaty. They had a compromise. They said that okay, Julius Caesar is elder and Augustus Caesar is younger. So let us follow the order and keep Julius the 5th month and keep Augustus the 6th month. So this is how you have a lot of history for your calendar. Okay. Later on,
calendar people died.
Yeah, they had a war. People died. Okay. So this happened there. You will find it in Google. Find out the history. See, calendar is just a piece of paper hanging on your wall, but the amount of history and astronomy that lies in that is unbelievable. You will be amazed. I am only giving you a short version here in today's program. I can talk for 2 days on the calendar itself and what things have happened and how the calendar what we follow today has been created. Okay. So what happened? Later on, another thing happened. Okay. They said that see, Janus, the god of the sky, is the god of good luck. And you cannot have the year starting in March, which is Mars. Mars is the god of war, god of blood, god of fighting and revenge. So let us not start the year on a negative tone. Let us start the year on a positive tone. So suddenly they shifted the month January to the 1st month. Automatically, February became the second month. So see, here it happened like this. Okay, these 2 months, January and February, came here on top and automatically March became the 3rd month. Okay, so when this happened, something strange got created. The 7th, 8th, 9th, 10th month, 7th, 8th, 9th and Des became 9, 10, 11, 12 and until this day, the month November means 9th month, but actually it is the 11th month. You just look at the calendar and these things will be, strange things will appear to you. Okay, this is how our English calendar has been framed. Later on, 400 years after the Roman calendar was perfected. Suddenly, not 400 years, almost 1,000 years afterwards. Okay, what happened is a geographer, a mathematician called Saint Bede. He was a saint also of the Catholic Church. So Saint Bede did one calculation and proved to the Pope Gregory the Eighth. Okay, proved to the Pope that this calendar also what we are following is wrong. If we continue following this, because of the leap day which is added, the seasons will again change. Okay, so what happened is for 1 year to correct the mistakes of the past 1,500 years, a strange thing was done. They dropped 10 days in October. Okay, they dropped 10 days in October, and next year they added 4 days in October again. So 1 year October was of 20 days, and next month October was of 34 days. It strange thing happened. Okay, in the year 1582. It is because Saint Bede had pointed out it is wrong. So Gregory the Eighth, the Pope, corrected the calendar and made 20th October. But immediately Aloysius Lilius, another mathematician, recalculated the whole thing and pointed to the Pope that there is another mistake. You should only drop 6, not 10 days. So again 4 days were added to October. Okay, so how fascinating the things are becoming. Finally, in 1583, Pope Gregory decided that now we will correct and make a permanent calendar and see that there is no changes again and again. So in the year 1583, a lot of astronomers, geographers and mathematicians were called a big conference in the Vatican. Okay, and the Pope made a new calendar which was implemented in 1583, and that is called the Gregorian calendar. Okay, after Pope Gregory. Okay, Gregorian calendar. These are called the calendric reforms. And till today, when you are seeing the calendar January to December, they follow the Gregorian reforms of Pope Gregory. Some people call it the Christian calendar, but now it is called the civil calendar. Okay, yes. So what is the rules? What are the rules of the civil calendar? Okay, the rules of the civil calendar or calendar are the calendric rules. There are 5 rules. Okay, the rules are that this calendar follows 31 and 30 days intervals. 31, 30, 31, 30, 31, 30. All the months will be not equal. Okay, the second rule is that all the years divisible by 4 will be a leap year. For example, 2016 is divisible by 4, fraction, so it is a leap year. A leap year is not a leap year just because it comes every 4 years. Remember, it is only leap year because it is divisible by 4. The third rule is that every year which is round 100, 200, 300, 2000, 4000, 5000 will not be a leap year. Even if a leap year falls, it will not be considered a leap year unless that year is divisible by 400. So 100, 200, 300 cannot be a leap year. But the year 400 is divisible by 400, so it is a leap year. 500 is not divisible by 400, it is not a leap year, and so on. Okay, so similarly, the year 2000 was a leap year because it is divisible by 400. But in 1000 years, in 100 years, the year 3000 will not be a leap year because it is not divisible by 400. So this rule of division, the rule of 4 and 400 applies to the Gregorian calendar. These are rules made by Pope Gregory in the Gregorian calendar reforms. Okay. The fourth rule is that this year shall have 365 days, 5 hours, 49 minutes and 12 seconds. But for the convenience, we will drop the 5 hours, 49 minutes and 12 seconds and collect them every 3rd year and make the 29th February. The leap day will be added exactly at the point where the Romans added the leap month after February. That is 29th February. This is the rule of the calendar. Okay. And the 5th rule is that this calendar will follow 2 ages, eras. One will be BC and one will be AD. Everything on planet Earth will be calculated in 2 time frames. One is the BC, before Christ, and one is AD. Okay, what is AD? Can anybody tell me? This is
So after crime.
So after that,
no.
Anno Domini.
Wrong.
So Anno Domini.
Anno Domini. It is wrong. Okay. BC means before Christ. Okay, before the birth of Christ. AD means not after death of Christ. Because what would happen? See, Christ lived for about 30 years, I think. So before Christ, one, and after Christ lived for 30 years, then AD after death. What would you do for 30 years? Would there be no calendar for 30 years? Tell me. When would Jesus celebrate his birthday every year if there was no calendar? Okay, so that is why remember BC means before Christ, before the birth of Christ, and AD means it is Latin. It means Anno Domini. Anno Domini means after the year of our Lord. Okay, Anno Domini, after the year of our Lord. Which is the year of the Lord? BC. The birth of Christ is the year of the Lord, and the next year is Anno Domini, after the year of our Lord. Okay, so these are different things related to our calendar. Okay, very fascinating, no? So I think we will wind up today. Not all this. So today I gave you a small gist of the calendar. It is already 8:30. So if you have the time and the patience, okay, you can sit down and enjoy two small videos which are related to this program. And after that, if there also you can ask. Okay, so I will just play those videos. These are live streaming, so they might be slightly slow.
A long time ago on a faraway island, the people kept time by sunrise, sunset, and the cannon. Every day at noon, on the hill above town, soldiers would set the pace in the village below. One day, a boy wanted to know how the soldiers knew when to fire. The artilleryman told the boy he gets the order from the captain. When he asked the captain, he said he keeps his watch synchronized to the great clock in the village. And when the boy asked the watchmaker how he sets the great clock, the watchmaker said, I set it to the noonday cannon. The way we tell time isn't so different today. The cannon and soldiers have been replaced by tiny machines, but somehow we've all agreed to agree when exactly is now. So who decided what time it is everywhere? Time in the physics sense is very real. It's what makes now different from then across the universe. But time, in the sense of hours, minutes, seconds, and you and I agreeing you're a half hour late for lunch, we made that up. The rhythms of time are built into our bodies, and most living things instinctively obey daily or yearly cycles by following the big, bright daytime sky thing. For most of human history, the sunrise, sunset, and some seasons were all the timekeeping we needed. And maybe going halfway in between for lunch. And maybe the tides if you're the Saxons. The first calendars were made to please the gods, and cows and crops didn't need clocks. But with civilization came schedules. People had meetings to make and employees to manage. Egyptians made the first clocks using shadows and split the day in 12. But that doesn't work in the dark, so Egyptians marked nighttime hours by watching 12 of their favorite constellations rise. Why 12? Because why not? Egyptians preferred duodecimal numbers to match the lunar cycles in a year, or maybe the finger joints on each hand. But either way, that's how we got a 24-hour day. Or they might have stolen it from the Babylonians. Ancients eventually switched from watching stars to watching water drip, but hours weren't a fixed length until Greek astronomers decided to make it that way. Later, Greeks decided to divide up circles into a very random 360 degrees, and each degree into 60 smaller minutes, and each of those into 60 smaller seconds. Why? Greek astronomers borrowed a lot of their math from that they borrowed from the Sumerians. Circles, so why use minutes and seconds for time too? What's clear is the 24-60 system doesn't make much sense. It's just how it happened. Water clocks spread all over the world and became pretty sophisticated, adding bobs and gears to show the water level and time on a face. But Europeans were the first to get rid of the water entirely and just use gears and gadgets, mostly because Europeans did extremely accurate time measurements to do experiments. Science molded clocks into intricate counting machines. Just figure out some regular wiggler like Galileo's pendulum or Christian Huygens' spring and count the wiggles. Congrats, you're a Time Lord, Harry. This new precision time created a new kind of human day. People knew when to go to work and when to move. More and more people disconnected their day from nature and turned it over to machines, which sounds kind of familiar. By the Industrial Revolution, schedules could be regulated to the minute, workers were slaves to the clock, and productivity was measured by what you made in how much time, because after all, time is money. This was a huge human history. Clocks even revolutionized exploration and fueled the colonial era. Precise longitude measurements require precise clocks. Sailors sync fancy new spring watches to a master clock at Royal Greenwich Observatory so they'd always know where and when they were. But remember that noonday canon? Accurate timepieces don't work if you don't agree on whose clock has the right time. Cities and companies would often follow their own clocks, choosing 12 noon to be whenever the sun was overhead in their city. Trains and telegraphs made this a problem, so in 1884, President Chester A. Arthur held a conference where the world decided, once and for all, what time it is. England was like, hey, we got that awesome clock in Greenwich. Everyone agreed Greenwich Mean Time would be the time, adjusted for time zones, which are a whole other thing. In the 1900s, scientists started using electronics to keep time. When quartz crystals are hooked up to special electric circuits, they vibrate 32,768 times every second. Tinier wiggles in a spring or pendulum, but same principle. Most of the gadgets we tell time with today use these little crystally wigglers. But clocks got so good, the definition of a second was now less precise than the things measuring seconds. The lengths of days and years aren't always exactly the same. The tug of the moon, earthquakes, gravity from other planets all tweak Earth's rotation ever so slightly and shift the year by a few seconds every few thousand years. It doesn't sound like much, but precise science machines like GPS and particle colliders need accurate measurements down to billionths of a second. The solution was to change the definition of a second. Unlike springs and pendulums, atoms wiggle pretty much the same everywhere in the universe. Today, atomic clocks count the wiggling of electrons in atoms, a little over 9 billion electron oscillations of a cesium atom per second, to be exact. And they're so precise, they may drift just 1 second in tens of millions of years. The Babylonians would be very proud. Nice. And probably think we're wizards. Today, our clocks work so well that we completely take them for granted. Yet it took more than 3,000 years with Egyptian priests and Galileo and even Chester A. Arthur all working together to synchronize the world. But they did, and now we can finally rest knowing that some magic machine knows exactly what time it is. And as always, thanks for watching.
Okay, so I think you got a whole gist of it, right from the, what I can say, right from the period of sundials, we have come to the period of the atomic clocks. Okay, so time is a very fascinating thing and a very important thing in astronomy. It's an extremely important thing. There's an entire branch of astronomy, dedicated to it. It is called horology. So it is a very, very intense thing. The science of time. So we will see a little bit of the calendar. Okay.
Celebrate January 1st as the new year. Why are half of our months named after numbers and the other after Roman religious practices and leaders? Have we always counted days, weeks, months, and years like this? What's with that Mayan calendar thing? There were a number of calendars in early human history. You had the Hebrew calendar, the Egyptian calendar, the Greek calendar, Chinese calendar, Babylonian calendar, and others. The one we use today in the Western world originated from the Roman calendar. Incidentally, the early Roman calendar evolved from that of the Greeks. It was basically a lunar calendar with an extra month inserted every so often to keep the months in step with the seasons. They were named Martius, Aprilis, Maya, Junius, Quintilis, Sextilis, September, October, November, December, Januarius, and Februarius. These names have pretty much been the same since the past 2,500 years. Unlike today, the Roman year began with March. The calendar consisted of 355 days, which was about 12 lunar months. The intercalary month, Mercedonius, was added when needed at the end of February. So when that happened, February was shortened to 23 days. Julius Caesar took it upon himself to bring the calendar in line with the seasons. He ordered 3 intercalary months to be added at the end of the year and rearranged the length of the months, giving them their present duration. He eventually rejected the lunar month entirely and adopted the solar year, which had an average length of 365 26.25 days. The 4-year leap year cycle was added to resolve the 25th of a day. The reforms took place on January 1, 45 BCE. This changed the beginning of the year from March 1st to January 1st as we know it today. The calendar was called the Julian Calendar for obvious reasons. The 7-day week was followed by Judaism and Islam. The week was set around a day of rest and religious practices. Romans didn't have a day of rest, so their 8-day week cycled around market days. Eventually, astrologers assigned a planet to rule each of the 24 hours of the day in continual sequence. This led to the Roman 7-day cycle. Saturn, the Sun, Moon, Mars, Mercury, Jupiter, and Venus became Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, and Friday. The names of the first 6 months are partially derived through the fact that certain Roman gods had feast days or times centered around them. For example, Janus was the god of beginning, so January was used for the name of the first month of the year. The month of March was the time that soldiers would begin war, so it was named after the god of war, Mars. The other 2 months were named after Roman leaders, and the rest of the months were just named after the number of the month that they were. October, 8th month, November, 9th month. The Julian calendar was simple, which made everything seem fine and dandy, but there was a small problem, a problem that added up every year. The 365.25 day year is 11 minutes and 15 seconds longer than the true length of the tropical year. After 128 years, the season begins a whole day earlier. The Egyptians, Greeks, and Romans didn't have an issue with days not lining up perfectly, but the Christian church did. You see, they wanted to make sure that the religious holidays they celebrated were on their actual days. Pope Gregory XIII took it upon himself to resolve this problem and came up with the Gregorian Calendar. The changes he enacted resolved the shift at the beginning of each year, set a standard for the length of a year in days, minutes, and seconds, among other things. The changes were not accepted in England and the British colonies in America until 1752. By then, the English calendar was off by 11 days compared to the calendar of continental Europe. Because of this, dates of events such as the timeline of historical figures will often have 2 dates. The Gregorian is called the New Style, and Julian the Old Style. The birth of Isaac Newton was the 25th of December, 1642, in accordance to the Old Style, but was the 4th of January, 1643, in accordance to the New Style. In the Middle Ages, New Year celebrations were abolished due to their pagan origins, but celebrations were started again in 1582. The modern calendar can't be credited to one specific person. It's pretty much the Gregorian calendar, but with an addition of dates for Christian celebrations and the way years are numbered. Oh, and about the 2012 Mayan prophecy stating the end of the world, don't worry about that, it's a bunch of bunk.
Okay, so that's it for today. I discussed about new topic. If people have already attended the past programs in the last year, it is not new to you, but for others it will be something new. And this is exactly somewhat there in the 9th standard. The 9th standard second lesson is on time, and this is mostly there, the synodic, sidereal, technical, little bit technical. But there is so much interesting things to astronomy, which I told you right now, okay? So yeah, somebody has raised your hand. Can you tell me? Yeah. Anybody? Any questions? I'll check. Okay. Is it true that due to precision, the time of the season of the Earth change? Yes, it is true. Okay. Then what other questions are there? Okay. Is there also a Chinese lunar calendar? Yes, there is a Chinese lunar calendar, and it follows cycles of years. I think 12 years or 11, I'm not sure. I think 12 years. And each year is named after an animal. The year of the pig, the year of the rabbit, and so on. Okay, year of the tiger, year of the bull, and so on. Okay, so fine. Those are all the questions here answered. Any more personal questions? I mean, direct questions here? Direct from anybody? Nobody? Okay, so
No, sir.
okay, so it's nice having you again on the program. This Saturday we are having a very, very interesting thing. There will be an astrophotographer who will be coming on the show, Rishikesh Shetgaonkar. He has traveled to different observatories around the world, and he will be showing you a beautiful slide, his photograph, his experiences, and any questions you have about careers in astronomy and all, astrophotography, how things are photographed in the sky. He will be there for you. So see you all on Saturday. Time is same 7 o'clock. Until then, good night and take care. Bye.
Bye, sir. Thank you.
Bye, sir.
Good night, sir.
Thank you, sir.
Thank you. Thank you, sir.
Bye,
Thank you,
sir.
sir.
Good night. Bye, sir.
Thank you,
Good
sir.
night, sir.
Thank you, sir. Bye, sir.